So, welcome everybody, and we'll begin. Today we're going over exercise 3F. It is rates of change. This is a beautiful exercise. It's going to be very easy compared to what we've been working through. And this is a skill where we can really just put some stuff in our calculator, do some G solving, a little bit of calculus involved. Okay, so all we're doing is rates of change, and we have, if f of x is a function, then f dash of x describes the rate at which f of x changes. So let's have a look at our first example. We have the height of a tree is given by this equation. H of t equals 12 on top of 1 plus e to the power of 5 take away t. This is the height of a tree in meters, where t is time in years. Now there will be a question like this in the test. Okay, so, and what it's going to involve, lots of just 1 minute, 1 mark questions that involve just G solving what's going on. We can do some of it manually. We're asked how tall is the tree initially? So that means when time is 0, what would be the height of the tree? And so all we would be doing is putting 0 into the equation and evaluating that. Okay, that's going to give us the height of the tree in meters. However, I'm looking at this question and I'm going, look how much calculations we've got to do. Let's graph it. We've got to choose an appropriate domain for it, and then we can start to perform the G solve. So we're going to go into our graph mode. And our function is 12 on top of 1 plus e to the power of 5 take, and we use x to substitute for t. And I've already got in there my first derivative and my second derivative. All right, so when I'm graphing this function, that doesn't look quite right. What's going on there? 12 on top of, I've got 2 x's at the bottom. I've got xx. So there we go. All right, so I'm looking at this function. I can see it skyrocketing up. Now, I should only consider positive values of time, right? It doesn't make sense to think of going backwards in time because we have since the tree is planted. So that means I'm only considering positive values of x, and we don't really know what an appropriate value for x is. So anywhere from 10 to 100 is fine. 50 might be a good one. And then as far as y goes, there is a way we can see what y approaches from looking at the equation. But to start with, just have a bit of a guess, okay? So you can just start by setting your v window to standard. But if I just type in 10, okay, we can see it's getting close, but I need to crank y up a bit more. And we can also see that my x value is plenty large enough, even perhaps too large. So I'm going to crank y up to 20. All right, just double it so we can see further. All right, and I can see that it's approaching a limiting value there. Now that I've got this graph in view, now I can G-solve everything. Be careful with G-solve because you can only G-solve what you're observing. Okay, you can only G-solve within the confines of your V window. So it does make sense to just zoom right out. All right, if you zoom right out, you don't need to have a perfect V window. It just needs to be approximate such that you can G-solve everything. Okay, we want to know how tall is the tree initially. That means when time is 0, what's the y value? What's the height? So we're doing trace, we're putting in time is 0, and I've got h of 0 equals, and we've got 0.0803. All right, I'll talk about significant figures here. So I'll talk about 2 things. When we're writing significant figures, okay, it's the first 3 non-zero numbers. Okay, so here's a 0, here's a 0. Okay, 1, 2, 3. They're going to be my 3 significant figures. 1 does not round up, it rounds down, and so h of 0 is 0.0803 meters is our unit. Okay, so 2 things. We've stated it to 3 significant figures, and we've stated the units. The height when time is 0 is 0.08 meters, 8 centimeters. Okay, after 6 years, this means What's the height when time is 6? What's h of 6? So we're still in trace mode. We'll just type in the number 6 and it'll bring it up for us 8.772. All right, so I'm going to write 4 figures and I'm going to do this all the time. I'm going to try to do it all the time for you guys so that you can get familiar with my habits. So I'm writing 4 figures and I'm rounding the 4th one, 8.77 meters. Okay, after 6 years. All right, discuss what happens to the graph as t approaches infinity. So we're going to do this 2 ways. We're going to do this from our graph and then we're going to make a mathematical argument as to why that's the case as well. All right, as t approaches infinity, we can just trace along it. And if I'm tracing along, okay, as x increases, as x increases, what's happening to that y value? Look at that, 11.99999999999. Okay, it's reaching 12. Okay, and that's just the calculator not evaluating it to the correct amount of significant figures. So what's going on to answer part B? As t approaches infinity, the height approaches 12. Okay, we can see that from our graph. We can see we've got this horizontal asymptote there. Now, I want to describe to you mathematically why that's occurring. All right, let's consider this function. We have 12 on top of 1 plus e to the power of 5 take t. I'm going to break it down. All right, we have 12 on top of 1 plus e to the 5 take t. I'm just going to talk about this part. What's this part approaching? So if we have e to the 5 take t, and let's consider as t approaches infinity, like if I put 1,000 in here, I would have e to the power of 5 take 1,000 as e to the power of minus 995, all right, which is 1 on top of e to the power of 995, which is 1 on top of 2.72 times 2.72 times 2.72, 995 times, right? So we have this enormous number at the bottom, and we have 1 divided by an enormous number. This whole thing is approaching 0. It's approaching 0. This part is getting closer and closer to 0. So if this is approaching 0, then the function is approaching 12 divided by 1, 12. Okay? So that's how we can make a mathematical argument for it. But I think this is a 1-mark question. You look at the graph and get it from there. Okay. Part B done. Part C. All right, here we are. At what rate is the tree growing initially? Now, I'll do 2 things here. Firstly, I might need to fix this question. We should find the derivative. All right, so in the test, we've got a question a bit like this, where it gets you to first find the derivative and then hence talk about the rate. So maybe wherever you can find some space, I think, wherever there's some space, we're going to find the derivative of this function. Okay, so we have 12 on top of 1 plus e to the power of 5 take t. I'm going to show you how we differentiate it. We could use the quotient rule, right? You've got a function at the top and a function at the bottom, but we don't need to because the function at the top is just a number, which means we can use the chain rule. I can take that whole denominator to the top. If you want to use the quotient rule, that's fine, all right? But I can take that whole denominator to the top to the power of minus 1. And now when I differentiate it, I'm just using the chain rule, all right? H dash of t, about 12 just hangs out the front. It's just a number that's multiplying through. And so then I'm looking at this function to the power of n. Function to the power of n. So the derivative is going to be n, the function, to the n take 1. N f of x n take 1. Okay, this is the chain rule. And then that's multiplied by the derivative of the inside component. So the derivative of 1 is 0. The derivative of e to the 5 take t is minus e to the 5 take t. Okay, so that's our derivative function. All right, we've calculated that there. And now we're just going to refer to our calculator. All right, so h of t tells us the height with regards to time. Remember, here's a question for you. F of x is the function, tells you the corresponding y value. F dash of x describes the rate at which f of x changes. So what does h dash of t tell us in the context of this problem? So f dash of x is the rate at which f of x changes. H dash of t is going to be the rate at which the
Tree grows.
the rate at which it grows, the rate at which the height changes. Very good. Excellent. So that's h dash of t. Let's go on to answer C part 1 and C part 2. At what rate is the tree growing initially? This means when time is 0, what is the derivative equal to? It tells you find h dash of 0. So we could put it in here, but that'd take a long time. All right, you can see we've got to look for what's the fastest way of doing things. In our calculator, we've got the derivative mode turned on, hopefully. I don't, I need to turn it back on. Turn derivative on. All right, and now when I trace along, when x is 0, what's the slope? dy on dx, 0.0797. H dash of 0 is 0.0797. Okay, so state it to 3 significant figures, but then we need a unit. All right, a unit for the derivative is always y per x. Y per x. What do we have on the y-axis? Height in meters. Okay, so meters per, what's on the x-axis? Time in years, meters per year. And of course that's true, all right? If the height is in meters, all right, the rate at which it's growing is going to be meters per period of time, and our period of time is years. All right, so that's initially, and then after 2 years, we want to find what's h dash of 2. So type in the number 2, and I've got 0.5421. All right, so I'll state to 4 figures, and then round, meters per year. All right, we've got next, when is the tree growing at the fastest rate? That means, when is the rate of change maximized? All right, so the easiest way for us to do this is to graph the derivative. Whoop. So I'm going to graph my derivative, turn my original function off. And remember, I like to graph just one function at a time because that allows me to G-solve very quickly. And we're interested in the max, isn't it? We want to know, when is the rate maximized? The rate is maximized, and answer the question, we're asked when. When is the rate maximized? When is the tree growing at the fastest rate? Our answer to part D is when t equals, and what's our x value? 5. So after 5 years. Okay, we'll accept both of these when t equals 5 or after 5 years. All right, now I want to point something out here. I really want to stress something because this is a skill that we just test over and over and over again that pops up in tests and exams. Points of inflection on the original function correspond with turning points on the derivative function. Okay, this is the graph of the derivative function. We have a turning point when time is 5. What does that mean about the graph of the original function when time is 5? Okay, let's have a look. All right, and I'll sketch it to exaggerate it for you. This is what the function looks like. Okay, when time is 5, points of inflection on the original function correspond with turning points. This is a point of inflection, concave up, okay, opening upwards, a cereal bowl, opening upwards, concave down over that interval. All right, so that's a feature that we will stress, that will pop up a fair bit. Okay, next question. All right, this one's got, we're going to do a little bit of, bit more calculation here manually. So, let's graph it as well. So we have the volume of water in kilolitres in a tank. Kilolitres, 1,000 litres. T minutes after the valve is open. So we're opening up a valve and the tank's getting emptier and emptier. So we have minus ln of, and then let's open up a couple of brackets. We've got 0.1, and then we'll open up another bracket, t plus 0.5. So I'm just graphing the function as it's been given to us. Okay, there it is. Minus ln of 0.1 times t plus 0.5. Now please make sure you use the double brackets here, and I should write that on in our notes book here. All right, so we're going to graph this, and okay, good, that's good. Now let's think about the context of this problem. This shows me volume in a tank. So when I'm considering this graph, all right, and it looks a bit like this or something. What are these values? Okay, on the y-axis I have volume. So then what's going on here? It's negative. It would tell me that I've got negative volume. We can't have negative volume. That doesn't make sense. The model has a limitation. At this point in time, the tank is empty. There's no water in it. And so that's our restriction for x. It's going to exist between these 2 points. All right. Nonetheless, we don't need to change our v window because we can g-solve everything from here. We've got everything we need there. Okay, how much water is in the tank initially? Let's go for trace when time is 0. All right, and the y value is 2.995. All right, so this is the volume when time is 0, 2.995, which equals 3. All right, 3.5 rounds up, which makes a 9 round up, which makes a 9 round up, 3 kilolitres. Okay, when is the tank fully empty? Hence state an appropriate domain. So one way we could do this is just g-solve the root. And we can see that occurs when time is 9.5. All right, sometimes if you push your v window down, you can see it a bit better. Oh dear. Oh dear. Anyway, 9.5. All right, so we can get that from there, but let's recap those log skills. How might we do this manually? This is the volume minus ln of 0.1 of t plus 0.5, and we want to know when is this volume equal to 0. All right, so the first thing we can do is just get rid of the negative. All right, so we can divide both sides by -1 or multiply both sides by -1. It's just going to keep it as 0. If you want here as well, you can distribute the 0.1, like we may as well do that, plus 0.05, and that's going to equal 0. Okay, now we're solving for t, which means we're going to raise e to the power of both sides. All right, so I'm going to raise e to the ln and e to the 0. And e to the ln allows me to get rid of the ln, right? On this side we'll have 0.1t plus 0.05 equals e to the 0, 1, and now it's a linear equation. 0.1t equals 1 take away 0.05, that's going to be 0.95. All right, and then divide both sides by 0.1. Now, one thing you should know by now is that multiplication and division are the same thing. 0.1 is the same as 1 on top of 10, yeah? And so, like, if I'm looking at this myself as a maths teacher, I'm going, okay, 0.1, that's 1 on 10, and so what do I need to do to both sides is multiply both sides by 10. All right, and that's going to give me t is 9.5 as we g-solved it. Okay, let's answer the question. When is the tank fully empty? The tank is empty when t is 9.5. Hence, state an appropriate domain, okay, for the volume function. Well, the volume function is going to be valid between 0 and 9.5. Time is in minutes. Okay, what is the volume after 4 minutes? All right, so now we're just saying when time is 4, what's the volume? V of 4 equals 6 point, I'm going to just fix my window. All right, when time is 4, the y value is 0.7985. So the volume when time is 4, 0.7985. 795, which is 0.799, okay? So, right 4 figures, 5 rounds up, which means 8 goes up to 9. Volume is in kilolitres. So volume after 4 minutes, there we go. When is there 1 kilolitre of water in the tank? So this question, this part here is very similar to what we did here. The question is, we won't repeat the whole thing, but it's saying, when is the volume here equal to 1? All right, and we could repeat that process to solve through fatigue. Let's use our calculator. We want to know when. When is a question about time. Time is on our x-axis. So we're going to go G-solve, and now we're not just tracing along, we're doing an x-calc. We want to know when is the volume, what's the volume? 1. All right, when is that? We've got 3.178. So if V of t equals 1, then t equals 3.178, which is 3.18 minutes. Okay, that doesn't mean 3 minutes and 18 seconds. That means 3 minutes and 0.18 of a minute. Okay, so that's our answer to D. If you want, you can make this argument here. In a test, it'll be very specific. If it wants you to find an exact answer, that's when you have to perform the algebra. A lot of the time, it's just a small space, 1 mark, just doing a G-solve. Okay, at what rate is water leaving the tank? And we've got initially, and then we've got when t is 6. So this is where we can use our derivative function, or we can just refer straight to the calculator. So let's trace along it, and we want to know what's the rate of change when time is 0. All right, we've got -2. So to answer here, part E, part 1, V dash of 0. The rate at which volume leaves initially is -2. And then our units, what's our unit? Kilolitres per minute, okay? Y per x, we've got kilolitres on the y-axis, volume, and minutes, time in minutes on the x-axis. Okay, part 2, what about, at what rate is water leaving the tank when time is 6? So we'll just trace along when time is 6. It slows down, so we have V dash of 6 minus 0.4307. Okay, 4 figures, 7 rounds up. So we'll have minus 0.431 kilolitres per minute. So we have V dash of 0. Oh, minus 0. I've written the Y value. Thank you. So that's minus 0.153 kilolitres per minute. Okay, so that's an easy mistake to make. Make sure you don't do that one. All right, so we're almost done. That's when water is leaving the tank. And let's talk about what's happening here, okay? So there's a big tank of water. You've opened up the valve and water's gushing out. And look, when you open the valve, look how fast it's flowing out. It's just pouring out. It's just raging out. And then as time goes on, the rate at which it's coming out starts to slow down. This is what you expect. If you've opened up a tank, there's heaps of pressure inside, all that weight of the water is forcing it out. Okay, so we expect that to be the case. Part F, there is one more part. The question is, when is water leaving the tank at the fastest rate? So this means, what is the largest value of V dash of t? When is the volume maximized? So let's have a look at our derivative function. And we've got to have a bit of a chat about what's going on with this function. Yep, so just the first derivative. And I'm just going to trace along it from when time is 0 to show you what's going on. All right, so when time is 0, all right, now because this is our derivative function, the y value here is telling us the rate of change, right? So we've got when time is 0, the y value is -2. And as we trace along it, we have when time is 0.39, the y value -1.1, so it's smaller. And when time is 0.77, it's smaller again, and it's smaller again, and it's smaller again. And so as time goes on, the rate of change just gets smaller and smaller and smaller. And so to answer our question, when is water leaving the tank at the fastest rate? Well, that's when time is 0 initially. So V dash of t is maximised. Water is leaving at the fastest rate at t equals 0. Okay, so I really want to encourage you with this exercise to use your calculator. I've demonstrated those skills there. I just want to mention one more thing. On page 53 here, we have a number of models that we often use to perform these rates of change functions for. So this isn't something you're required to know, but it can be useful if you want to explore that a bit further. We have logarithmic models, surge models, terminal velocity, and logistic models. And so you'll notice, like the first question we did about the height of a tree, it was a logistic model, that we had that horizontal asymptote occurring at C. It had that same form. You will see throughout this exercise surge models and terminal velocity models. So 3F, that's our plan today. Let's rip into that and